Hi folks, welcome to day 2 of our extra credit unit. Today we're going to be working out of 9.2. So 9.2 again is this continuation on right triangle trig, but the interesting thing about 9.2 is actually we're getting into some more about how right triangle trigonometry relates to the physical world. And so we're going to be dealing with things like new types of measuring angles. So instead of measuring we have our triangle here. This is not a very good triangle. I'm sorry for my terrible artist skills. But if we have a right triangle, normally we have an angle theta, and it's usually written in degrees, right? Well, today we're going to be learning how to transform or convert those degrees into something called radians, which is a unitless measurement of angles. And these come into huge play when you're working in anything that has circular motion or circular, that's just circular in naturally. So you'll have things like an arc sector of a baseball field, right? This is the type of problem that we would be working with in the physical world that 9.2 is going to teach us about. All right, let's go ahead and start with conversions though. So there's these unitless things called radians, all right? And really the basics of what you need to know is that they don't have any unit measures. Like degrees has a degree symbol, right? Kelvin and Celsius have K and C. So most of the time when we're measuring things, we have units. Well, radians is a unitless measure of an angle. All right? So that's all a radian is. It's just something that we use to measure an angle. And pi radians is equal to 180 degrees. And 2 pi radians is equal to 360 degrees. So in order to convert between radians and degrees, you multiply by pi over 180 or 180 over pi, depending on what you start with. All right? So if we start with an angle that's in degrees, we're going to multiply it by our first one. All right? So I'm going to say if we start in degrees, we're going to use pi over 180. And if we start in radians, then we'll use 180 over pi. All right? So let's go ahead and try out an example. So let's go ahead and convert 60 degrees to radians. All right? So I have 60 degrees. And since I'm starting in degrees, I said, okay, well, if I start in degrees, I'm going to want to use our first conversion. So I'm going to go ahead and multiply 60 degrees times pi over 180 degrees. The reason why we want to do that is because our degrees on top cancels the degrees on bottom. All right. Now here we have 60 over, so that this then is 60 pi over 180. All right. But 60 over 180 can be simplified down to 1/3. So then we can have 1/3 times pi, or you'll usually see this written as pi over 3. All right, so 60 degrees is the same thing as pi over 3 in radians. That's all you have to do to convert. And remember, to get from this step to this step down here, all I did was simplify 60 over 180. All right, and that's just 1/3. Let's go ahead and try one for y'all. All right. So if you have 50 degrees, go ahead and try and convert that. Try and convert 50 degrees. So to convert 50 degrees, you're just going to have to multiply by pi over 180. All right, just like we did. But then you'll have 50 over 180, right, or 5/18 pi. All right, so that one doesn't really simplify down to be like super nice in terms of like our first one was a super nice fraction. This one, it's not necessarily going to be like nice pretty fractions, like simple little fractions, but they're often going to be fractions like that. Let's go ahead and try one more. All right, for this one, I want you to try and convert negative pi over 12. All right, so negative pi over 12. All right, convert that. So that's in radians. Try and convert that to degrees. So your first step should be to multiply by 180 over pi. And the reason why you want to do that is because then your pi's on top, cancel your pi's on bottom. All right. So then you're left with negative 180 over 12. All right. Now with this one, since you do have a negative sign, technically you have two options. You can either give the positive answer, right, which is going all the way around. Sorry, I should draw that the other way. Going all the way around. This is what we'd consider a positive answer. Positively, this would be 405 degrees, all right? But I want to just focus on using the conversion, right? So we have 180 over 12. So that's the same thing as negative 15 degrees, all right? How you get the positive answer, all you have to do to get the positive answer is you know that it's negative 15 this way, right? So this is a 15 degrees. So you go around the circle once, which is 360. Go around the circle the extra amount, right? So that is something that you can do. However, I think it's easiest, right, is to just focus on using the conversions themselves. All right, I think that that's a lot easier than worrying about the positives and negatives. And that's just because it gets a little bit more complicated, and you need to learn a lot more vocabulary in terms of like why it is that way. So I think utilizing just the formula for now is all I want to focus on. All right, so 9.2 starts with conversions, and we learn how to convert radians to degrees and vice versa. Then we're left with two formulas, all right? So the two formulas we're left with are called arc length. Now an arc length, right, is just like a piece of a circle. That's all an arc length is one small piece of a circle. And arc length we call S, and it's equal to r theta, where r, right, if this is part of a bigger circle, r is your radius, all right? And theta is your angle, usually in radians. All right, so it's your angle in radians. All right? So that's what your arc length formula. You multiply your radius times your radians. All right? And then you have the area of an arc length, right, or the area of a sector. Because if we had like this is what we call the area of a sector, because it has like a partially rounded portion. And the area of a sector is 1/2 r squared theta. All right? 1/2 r squared theta. And that theta, again, has to do with, that has to be in radians, all right? That's why you don't see any pi's in here. Normally you'd see a pi based off of like how much of the circle we were taking, right? So 1/2 pi r squared would be half the circle. But this case, what's really great about the area of a sector formula is that you don't have to know exactly how much of the sector it is. Like you don't have to know if this is exactly 1/4 of a circle or 1/8 of a circle or 1/24 of a circle, right? You don't have to know that because you have this area of a sector and you have the radians. All right. So let's go ahead and try out a problem that utilizes these. Okay. So let's say we have a baseball field that has a radius of 200 feet. Okay. And it has a 90-degree angle. And let's say back here we have a fence. This is our outfield fence. We're trying to figure out how long that fence has to be. So this is an arc length problem. So I'm going to write S equals R theta. All right. So your R is always your radius. And your radius is always your straight length from the center outward, right? So in this case, our radius is going to be 200 feet. All right, so R is equal to 200. Now theta is currently 90 degrees, all right? But we're going to have to multiply that by pi over 180 degrees in order to get that into radians. Because remember, this angle has to be in radians, okay? So we have 90 degrees, all right, times pi over 180. So 90 over 180, well, 90 is half of 180, so that's 1/2 pi, all right? Or pi over 2 is usually how we write it. So then S, our arc length, all right, is equal to R. And remember, R up here was 200. So we have 200 times theta, and theta is 1/2 pi. All right. Half of 200 is 100, so we're left with 100 times pi. But remember, we are looking for an actual number. So multiplying these, we get about 314 feet, okay? So that's how you find that arc length. So now we're going to go ahead and find the area of this sector, all right? So we know that the area is 1/2 R squared theta, okay? So we know, we said that R was 200, and we said that theta was 1/2 pi or pi over 2. So for our area, we have 1/2 times 200 squared times theta, which is pi over 2. Okay? So the big thing here is this 200 squared, which is 200 times 200, which is 40,000. So we have 1/2 times 40,000 times pi over 2. Okay? So I have 1/2 times 40,000. All right, that gives me 20,000 times pi over 2. All right, multiplying by just the over 2 part, or multiplying again by another half, we get 10,000 times pi. And we're left with the total area of about 31,414 feet. All right, so that's our total area. It's 31,000, about, you know, it's an estimate, because like pi goes on forever. But that's what you get in terms of utilizing that arc length formula. So now let's go ahead and have y'all try one out. All right, same type of problem, but all right, what if instead you were working with a t-ball field? All right, so this is now a t-ball field, still 90 degrees, but I want you to try and find the arc length. All right, try and find this S, and try and find the area. All right, well, that's all I have for you today. Those were the main concepts from section 9.2 is knowing that you have to convert from radians to degrees and vice versa. And then these two formulas, arc length and sector, area of a sector. All right, remember, don't worry too much about trying to like draw these. Mostly focus on the fact that these are formulas to utilize. All right, that's all I got for you today. Thanks for watching.